This is part 10 in a series of videos in which I am reproducing this ADM-3A main board. In the previous videos we got as far as getting the clock circuit, the dividers and the first part of the divider chain working. We then got the baud rate generator working, so all the baud rates work. We just got one IC to fit for the 110 and 1800 baud rates. But other than that, this circuit is fully working. And we also got the clear circuits working. And this is now all working fine. The next step is to move on to the display counters. So we have a series of counters here that are responsible for putting the data onto the display, and also to determine where in the memory location the current character is being addressed. So before we go into getting this working, I thought I'd just give a very brief run through of how these counters work in terms of how they are structured to allow the dumb terminal to display characters on the screen. So I'll get the board out of the way and then we'll have a quick look at the schematics, and I'll just briefly explain how the overall system works. So the heart of the system is a series of counters, and these counters all work together to determine exactly what is displayed on the screen. And the easiest way to explain the overall operation is to do a very quick run through of how the image is made up relative to what's in the RAM contents. So the way the screen is updated is, if this is the top left hand corner of the screen, and let's say we want to display the characters A, B, C on the screen, then as you probably know, the screen is refreshed by scanning from the top left hand corner across the first row down to the next row, across the next row. So if we imagine we want to display a character like an uppercase A, then as we start scanning from this location, then we have to determine what value we want to put onto the screen. So we can represent a bright portion of the screen, that's where the lines are, with a 1, and the dark portions with a 0. And that ultimately means that we can represent each portion of the character with a binary value. And this particular machine uses a character set that's 5 by 7. Although the characters themselves are only 5 pixels wide, they actually occupy 7 bits because there's a space between each character. And then the next line down will be another byte value, the next line down another byte value, etc. And that's how the character is built up on the screen. So for this to work, we need a series of counters. So if that was the first character and then the next character was the B that we want to represent, then of course the values required to make the B appear on the screen are not the same as the values required for the A. So the counters we need are a counter to keep track of where within this particular byte value or binary value we are as the screen is updated, as the scan is updated. And we also need to know which particular character we are looking at. We also need to know which line we're looking at, and that's in line by line for the entire character. And then if in the next text line down we wanted to put a C, we do of course need another counter to keep track of the actual character row that we have. Now the individual pixels are not, we don't need an actual counter for that, we just need to load a value and then shift that value such that it's displayed on the screen. We do need a counter for the particular character, and this is an 80 character wide screen, and so we need a counter that counts from 0 to 79. We then need another counter that counts from 0 to 6, which is her, so that will go from 0 to 6. And then we need another counter that counts the character rows. So that's what these three counters are. If we get the page out of the manual that shows how this is all updated, then we can see that this is exactly how the display builds up what's on the screen. So we have a dot count, which is defined within this system as DC. We have a row count, a dot row count, which is LC, and then we have a character position count, which is CC, and that's what these three counters are. So if you look at the designations for the individual lines in the counter, we have a CC0 to CC7, and that is the counter for the entire screen. We then have the character line counter, so that's counting these individual lines, and they're defined as LC0 up to LC3. That's a 4-bit counter. And then we have a 6-bit counter, which is for the character row count, and the character row count is the actual row of characters on the screen, and it's 6 bits because this display, this machine, will handle up to 24 lines of text. So they're the three counters that we need, and as I said, the individual pixels are handled slightly differently. So the way this is handled is we have a memory bank, which is our SRAM, and then we have the screen itself, and a given location in the SRAM maps to a particular location on screen, which is where the character will be displayed. But the individual values to make up the character are not stored in RAM. All that's stored in RAM is the value that represents the particular character we want to display. So let's say, for example, in the character set, an uppercase A is represented by a value of 41, then a value of 41 is what would be in the RAM. And then between the RAM and the display is a character generator ROM and a shift register. So as these counters progress and the system realizes it's just starting a new character, the first thing it does when it starts a new character is it uses the current count values to look up a value in the ROM. That value in the ROM is transferred into a shift register. The shift register is driven by our pixel clock, which is why we don't need a counter, and then those bits are shifted out of the shift register and put onto the display. So whatever's in ROM, let's say the value is 0110, is put into the shift register, and then on each cycle of the pixel clock, those values end up being transplanted onto the screen. When it comes to the next character along, then that value might, for example, be 31, in which case a value of 31 is used to select the correct value out of the ROM. That value is put into the shift register, and that value is then what is shifted onto the display for the next line in the next character. The whole screen then moves down one line and the entire process repeats. So in other words, the contents of the character ROM are moved into a shift register under the control of the counters, and then the pixel clock shifts the values onto the display, and this keeps repeating depending on the contents of the display RAM. Another set of counters determine where in display RAM we are currently looking at for the current character, and that's our cursor. So on the screen it's represented as a cursor location on the screen, but what's actually happening here is if we press a key on the keyboard, then depending on where the cursor counters are pointing, that's the character in RAM that will be updated. Or if we have some incoming RS-232 data, that is also put into the current cursor location in RAM. And then as the RAM is scanned and the display is updated, any changes are reflected on the screen as the character changes to whatever the character in RAM was changed to. So that's how all this works. If we look in the manual at the page that shows the counters, we can see the counters have different numbers of bits because they have different magnitudes of data to represent. We can see the frequencies we're expecting here, and the other thing that really complicates this is we can have two different refresh rates. We can either have 50 Hertz or 60 Hertz. So we'll look at that when we look at the board, and there's a selection switch on the board that lets us switch between these. But all that's really changing is we're selecting a different value at which the counter is reset. But all the other counters work the same. We have a counter to count which particular character on the screen we're currently trying to update, and that makes sure we pull the right value out of the ROM. We have another counter to make sure we've got the right character row, so that's the row within each individual character, and again that's to make sure we pull the correct value out of the ROM. Those two values work together, so if we look at the schematic for the memory, we'll see that we have the ROM here. This is slightly different to what's on the actual board we're looking at. I'll show you the schematic for our actual board another time, because I did have to redesign this because we're not using mask ROMs, but it works in a similar way. The lower 3 bits of the LC counter, which is this counter, and that's the one that counts the lines within the character. The first 3 bits are used to make sure that we select the right value within the ROM that represents a particular line within a particular character, and then the other address bits select the actual character value, and those two working together make sure that we can pull the actual value we require out of the ROM based on the line that we're trying to currently draw, that's the character line, and the particular character we're trying to represent. Okay, so that's how it works overall. If you want me to go over this in more detail, let me know. It does get fairly complicated, but let me know. I'll go over this in a separate video if you want me to. But it is fairly interesting, and it is pretty much the same way that display controller ICs work. It's just that most of this is normally built into the actual IC, whereas on this board it's all discrete logic, which is why it seems so complicated. Okay, so I've already fitted these components, and we'll now test to make sure that all these counters are working. So we'll start with the character position counter. So these are the CC0 lines, and what we should see here of course is just a binary sequence. So this is starting with component D15. So D15 is up here, and if we go across, what we should be seeing is a series of binary values. So I'll get the probe ready, we'll power up the board. And as you can see, what we have is a binary sequence, which is exactly what we would expect to see. So that's the character position counter. Next is the character line counter, and as ever these are spread all over the board, so they're not all in one location as you might expect them to be. So the character line counter is component K15, so that's this one, and again we should see a binary sequence. Now these are going to be going slower and slower of course, because we're scanning if you like larger chunks of the display memory. So I'll adjust the scope, and this again should be a binary sequence, which indeed it is. So in other words, the character counter is working, and then finally we want the character row counter, and this is D10 and C10. So D10 is this device, again this will be slower still, and indeed that is working. So all 3 main counters are working. I don't know if they're counting to the correct value, so what we can do is look at the output of C9, and this should be our 50 Hertz stop signal. So this is what causes the counter to effectively reset at the right period, and we can then look to see if we're getting the right frequency on the screen, and that will tell us if we're getting the right count value, because we know the frequency of the clock's correct. So what we'll look at now is pin 8 of C9. And as you can see, we are indeed getting a 50 Hz signal, which is exactly what we should expect for the 50 Hz display rate. So that's working fine. I'll just flip the switch over to 60 Hz and we'll see if we're actually getting 60 Hz working as well. So as you can see, I've fitted the dip switches and the sill resistors. So that's the resistors that control the switching for the various options. So now if we look at D8 pin 9, so as you can see, we're now getting 60 Hz, and that is the 60 Hz reset stop signal. So as I said, what these two components are doing is they're looking at the counters and pulling out the right count, at which point they reset the counter back to 0, and then it just runs back up through the same count, and this guarantees that it counts to the right value. And because it's working on both 50 and 60 Hz and we're getting the right frequency, and we know that the input clock frequency is correct, then we know that we're counting to the correct value. So I'll just put it back on 50 Hz and we'll recheck to make sure we're getting our 50 Hz count back. So that's D8 pin 10, and indeed we are getting 50 Hz. So this counter is working fine. So the next thing I want to look at are the circuits that use these counters to put the data onto the screen. So what I'm trying to do in terms of getting this up and running is I want to discount the RS232 to start with, because that involves connecting it to other things. I want to get it running autonomously first, and that means getting something that I can display on a screen. This is not going to be quite as straightforward as it could be, because obviously we've replaced the mask ROM with an EEPROM, so I'm going to need to generate some information we can put into the ROM to give a character set. I can't just download an existing character set because it would be the wrong set. I need to try and duplicate the set that we have in the mask ROMs. But initially I don't need to put anything into the ROM socket at all. It means we'll get nonsense on the screen, but what I want to do first is just make sure that we can get the screen control signals. And by the same token, I don't need to fit the RAM, although it means I can't modify what we're displaying on the screen. It will still allow me to test the counters and make sure that we are getting the correct drive signals for the display. So if we get the schematic for the ROM drive, so what we have here is, this is the RAM. It's not really shown very clearly on here, it doesn't even show the data lines at all. But these devices are the RAM chips, and they would normally hold the information that's used to determine which character to display in each location on the screen. And then the way that each character is displayed is by that value being latched into these two devices, and then as this is scanned by the clocks, the correct value for each location on the display is selected from the character ROM. That value is then latched into a shift register, and then the pixel clock shifts that value out of the latch, out of the shift register and through to give us our video signal. And it does that each time the line moves on to the next character, and then the counter resets and it starts counting again. And these three lines up here, LC0, LC1, LC2, are used to determine which line in the particular character we are currently trying to write to the screen. So these lines pick out the correct character, and these lines pick out the correct line of each character. So each character consists of 7 bytes within the ROM. So what I want to do here is to see if all this is working. So the first thing is we need to see if we are getting a clock signal coming through to the shift register. So I've already fitted these. I haven't fitted the RAM, and I haven't fitted the EEPROM, and I haven't fitted these. These are for taking the data and feeding it through to the serial port, so we don't need these at this point. But what I'm looking for here is to see if we are trying to shift data out of the shift register, and also if we're trying to load the shift register. So first thing is look at pin 7, and this is device K14, so that's this one, and pin 7. Again, very odd looking signal because I don't have the ground lead on the probe, but that's looking correct. We're getting the right frequency, and so we know that we are getting a pixel clock going to the shift register. We now need to look at the data shift register, that's pin 15. And a frequency of 1.56 megahertz is correct. I won't go into why that's correct, but you can calculate this, and it's really the rate at which characters are written to the screen. And if you calculate that for a 50 or 60 hertz 80 character wide by 24 line screen, you'll be able to calculate the expected frequency. But really what you're doing is dividing the 10.92 megahertz by a particular value based on the number of pixels in each individual character, or the width of a character. Okay, so that's working, and then what we can do now is look at the data values going to the shift register to see if we're getting any activity there at all. So in other words, what we should be seeing here is something on pin 13. If this mechanism is working, we won't be getting character information because there's no character ROM, but we should be seeing something on the output of the shift register. So we'll look at pin 13, and again that's K14, and again we are indeed getting something on the output of the shift register, and that's going to the video drive. So what we would actually see here on the screen, if this was directly sent to the screen, is a series of vertical lines, and obviously that's not the correct video, but that's because we don't have anything providing the actual video data. Okay, so it's looking extremely promising so far. All this is working, and the next thing I need to do really is to look at putting a ROM in the board. I'll program the ROM at the moment with all fixed values, so I can get a consistent signal coming out of it irrespective of the address that we put in, and as long as the data we're getting out of the shift register matches the value in the ROM, then we know that this mechanism is working. And the reason I have to go through this in multiple steps is because I'm not using mask ROMs. I've got a completely different circuit here, so I need to make sure that I've designed it correctly and that it can correctly read values from the ROM. So that's what I'll do in the next video. We'll get the ROM fitted, see if the system can shift data from the ROM out of the shift register to the video line, and from that point on we should be able to start looking at the RAM and seeing if we can actually display anything on a screen.